The Aurora Borealis, or Northern Lights, above Bear Lake, Alaska, make a spectacular demonstration of the Earth's magnetic field. In this lesson video, we're going to look into magnetic fields, how to draw them, and how to create them using electricity. But first, let's look at the big magnet underneath our feet. Inside the Earth, there is basically a big magnet. Obviously, it's more complicated than that, but the model works. The Earth, like all magnets, has a field around it. If we take a compass and put it near Earth, the north tip of the compass will point to a magnetic south pole, which is in the north. Someone messed up there obviously, but yes, the north pole of the Earth is actually a south pole. Let's look at a proper magnet instead. This classic image of iron filings around a bar magnet is probably very familiar to you. It looks a bit like Earth too. There are two magnetic poles here, north and south, the two opposites in magnetism. Like poles repel, opposite poles attract. Here, there are two magnets. One is obvious with its blue and red ends. The compass that is being moved around is also a magnet. The grey end, with the red arrow added, is pointing towards south, away from north. Remembering that opposites attract, that means the grey end is a north pole. Now, as the iron filings get put back in place, you can clearly see that the iron filings and the compass show exactly the same pattern. Let's do that another way so we can really see the pattern. You may need to describe how to do this. I'm going to put the compass at the north pole and draw a dot at the tip of the needle. Now I'll move the compass so its tail touches the tip and repeat. And again. Now, moving back near the end of the magnet, we do it again. Notice how this time there is a curve to it. As we keep going, I can build a full pattern. Notice how the lines never cross, but also notice how the lines are close together at the ends, at the poles, but more spread out elsewhere. What do you think this represents? Thinking about what you know about the poles. Magnets are strongest at the poles. That's where you pick up objects, isn't it? We can see that by looking at where the lines are closest together on this pattern. And there's the butterfly pattern of a magnetic field. That's all well and good, but we don't actually use that kind of magnet all the time. The problem with them is that we can't turn them off. Once these have been magnetized, they will stay magnetized, which makes them great for some applications, but rubbish for others, as we'll see later. If we change to a coil and pass electricity through it, we can get exactly the same effect. And we can turn it off. So let's look at electric fields created by a current. I want to start with a single wire like this. The middle part is copper with green insulation on it. Running a current through it, notice that we're going to use conventional current. So the current is flowing to the upper right. This is going to generate a magnetic field. It always will. The magnetic field is circular, going around the wire. Notice that the field, which we give the symbol B for some reason, is going up around the back of the wire and then down around the front. So up the back, round the front. If you were to reach out and grab the wire with your right hand, go to do it, your right hand, you should notice that your fingers would curl round the back of the wire in the same direction as the field lines. And your thumb points in the same direction as the conventional current. This is the right hand grip rule. and you're going to be using it whenever you want to know the direction like this. It only relates two things together, current and magnetic field. If we had any compasses, they would point in the direction of the field lines, just like before. Now this is the basis of so much of our electricity, but it's a bit weak like this, so we're going to need more electricity flowing. We could simply increase the current, and that's an important way to control the strength of a magnetic field. We could simply get more wires like this, as each one will have a magnetic field which will all add up to one big field. But if instead we take the wire and coil it up, we can get the same effect much more simply. Notice how the coil is always coming down at the front and up at the back. Well, it depends how you look at it, I suppose, but the point is the bits of wire at the front are all similar. If I pass a current in on the left, it flows down, then up, then down, up, down. The current is always going down at the front. That's going to be powerful because it's going to give us an electromagnet. Helpfully, all the magnetic field lines inside the coil point in the same direction. In fact, we can simply use the right-hand grip rule to see the direction. This time, see right hand, the current is going round, so that's your fingers, and the field is straight in the direction of your thumb. It's all to do with how the circular fields around the wire combine, as this cross-section view shows. But I don't want to overcomplicate things now. We'll come back to this later on, because we've already covered a lot about magnetic fields in this lesson. We've seen the shape of the magnetic field with the butterfly pattern that we get around a permanent magnet and around a solenoid. We've seen the magnetic field around the Earth, which can cause that aurora. And we've also looked at how a magnetic field is generated around a wire. What we need to do next is look at some applications.